and welcome to the IEEE Spectrum Online presentation, The Evolution of 5G in Future Releases and Its Impact on Testing, The Path to 6G. This webinar is also the fourth installment in our webinar series, The Road to 6G. I'm Dexter Johnson, and I'll be moderating this presentation. Before we start our presentation, I would like to mention a few housekeeping items for those of you using Chrome or Edge browsers. If you have Flash blocked, please click on the play button on the media player. If for any reason you have some difficulty seeing the slides or have some issue with your audio, just try to refresh your browser. This will fix just about any issue you may be having. For those of you who want to know if the session will be archived, the answer is yes, it will be archived and will be available for review within about 24 hours. And once the archived webinar is available, a notification email will be sent to all the registrants. Today, in addition to our presentation, we hope to have a Q&A session. We encourage questions from the audience, so as your questions occur to you, please type them in the Q&A box provided on your computer screen and hit the submit button. You don't have to wait until the end of the presentation to begin submitting your questions. If you're looking for the PDH certificate code, this will be given in a slide at the end of the presentation. As you look over your screen, you should also see buttons that allow you to enlarge the slides if you so desire. And about volume control, you may need to actually adjust the volume on your computer itself, not just through the platform. At the bottom of the slide in front of you are some additional widgets that will improve your viewing experience. And you should see a presentation link and a PDH certificate code form on your screen. Now I would like to introduce our presenter for today. That's Dr. Kevin Ramdas. He's been leading expert in the field of telecommunications for the last 20 years and has been on the forefront in the evolution of connectivity from 2G through to 5G. Kevin is actively involved with helping companies test and solve issues with communication products, platforms, and processes. He has also developed many courses to help professionals learn the foundations of telecommunications. He's a member of the 5G Council of Canada, TechNation, formerly the Information Technology Association of Canada, and the Institute for Performance and Learning. And with that, Kevin, I'll turn it over to you. Would you like to begin?
Thank you very much, Dexter. All right. So I'd like to thank everyone who's online here for attending. And I'd like to welcome you to this seminar. I'd like to thank IEEE Spectrum for hosting and for the invitation to speak, and Enritsu for sponsoring this talk. So we'll just get right in there. So this talk is part of a webinar series on the path to 6G. So when we're talking about this, we're talking about moving from 4G in release 8 through several releases of 5G, namely release 15, 16, and 17 that are released by an organization called 3GPP. So what is 3GPP? 3GPP is a set of standards organizations that help build all of the 5G technical specifications. They lay out the studies that are needed to improve the system, and then they organize the building of the specifications. The specifications for 5G are released in major releases. Hence, we have releases 15, 16, and 17, which are related to 5G technology. All of these releases, they come out approximately every 18 months to 24 months. In each release of that's coming from 3GPP, it can include drastic architectural advancements or just add functionality and improvements on previous released technology. So when we look at 5G, and pretty much all of the releases that are coming from 3GPP, it's set up to continuously evolve our communication networks to the next generation. So as we're looking at these steps for release 15, 16, and 17, we're slowly setting the foundation for possibly what we see as a 6G communications. it's important to realize that when we're looking at all of this 3GPP process, that it's an evolution of a system as opposed to a revolution. So it's not like we're cutting down a system and putting in a new system. All of these systems that we're talking about, all these improvements through the releases, what we're seeing is that it's part of a larger idea to improve the system. But in reality, when we're looking at the rollout of our systems, we're always bounded by the economics of rolling out the technology, which means that we're always implementing all of these new technologies or new ideas or whatever's coming out in the releases to on top of existing infrastructure that we have in legacy systems. So in many countries, we still are seeing 3G systems. There's 4G systems, and now what we're doing is we're overlaying 5G on top of the 4G systems. And that's just at this stage of development of where we're at. So what we'll hear about in this seminar is that we're going to see that 5G is an incredibly flexible set of standards or specifications that allow for many different implementations and implementation scenarios for carriers, users, devices, and networks. And if we get to a point where you start to understand the number of possible options for deployment, you'll appreciate the complexity of integrating all of these somewhat heterogeneous systems together. So questions will arise around how do we manage the complexity and ensure that the system that we build is robust and can achieve what seems like far-fetched requirements even just a couple years ago. In this seminar, I'm planning to talk about the requirements of 5G, just to outline the use cases other than high-speed internet or enhanced mobile broadband. In terms of 5G, this aspect is probably the most publicly visible part of it, that high-speed internet part. However, 5G is a little bit more than what's publicly facing, because on top of that, we're talking about massive machine type communication, which is IoT, and also vehicle to vehicle communication. And how do you integrate all of those things into the same system? What we'll look at, so 5G adds quite a bit to 4G systems, and we'll look at new advancements in the radio access network that allow 5G to solve many of the challenges that are presented in the 5G requirements. And when we look at the number of deployment options and new technologies and processes that are happening to ensure 5G systems are working, we'll see that there's a lot of work to do around optimizing 5G so that we can possibly reach 5G requirements and surpass them in the future. What I'll talk about in this seminar is the path that 3GPP is laying out for us through the releases, combined with machine learning algorithms that can be applied to certain scenarios and processes throughout the system to make sure that we have a more robust network and more energy efficient network and an easier to deploy and maintain network. Just to, always when you say what you're going to talk about, I'll talk about what I'm not going to talk about. So in here, we're going to talk about machine learning and AI, but machine learning and AI can be applied to so many things that on top of just the regular 5G optimization, it can be applied to additional carrier services or over-the-top applications. I'm not going to talk about all of those other applications. I'm going to stick to how do we use machine learning and AI to optimize our 5G networks. So let's start off talking about the 5G requirements. 5G has a number of use cases and frequencies that can be used. Generally, lower frequencies are used to provide coverage and are familiar to the operators around the world, since we've been using these frequencies for decades, from 1G through 4G. We've got mid-band frequencies, in and around that 3.5 gigahertz range that are the new 5G frequency bands. The rollout of this band is happening currently. And so when we're looking at 5G speeds and what 5G has promised us, consumers will start to see that these higher 5G speeds because of this rollout. So overall, when we look at this, it's being rolled out right now, it introduces some complexity for our carriers, because not only is it one of the issues that it causes for them is that they won't be able to reuse, they won't be able to only reuse the sites that they have. They need to build out a little bit more. And part of the issue that exists here is that as we move up in frequency from what we're used to higher frequencies, the higher frequencies are unable to propagate as far as the lower frequencies. So then now, when you look at the sites and the real estate that carriers already have, the 3.5 gigahertz band will only be able to cover part of that coverage. So overall, it'll make some sort of complexities or challenges with respect to deploying cohesive and ubiquitous 5G services and bandwidths. Next is our purple one, our high frequency cells. Those are in the millimeter wave. This is a new frequency set with very limited propagation characteristics, but it has a lot of bandwidth, which means that it can provide data rates that we haven't seen wirelessly before. Those sites will probably be used for hotspot coverage that require really low latency and a very high throughput. And when we put all of these different frequency bands into operation, it's possible to provide a communication environment that can support a tremendous number of use cases outside of providing decent mobile data rates, which we use for browsing the internet or streaming video. We're going to be able to add in low latency connections that are required for Industry 4.0, to providing machine type communications and running connectivity for millions of sensors in, I don't know, maybe smart city applications or something like that. 5G, when we look at all of this, all of these different requirements, 5G as a specification tries to address a number of these conflicting requirements that would be a challenge for traditional wireless systems. For example, in traditional wireless systems, you can't have both of these things. You can't have low power consumption and low latency connections, because for low latency connections, you need to be monitoring all the time. So you can't have low power consumption. You can't have high data rates and support a massive number of devices. All of these are conflicting requirements for one system. So when we look at 5G, or the vision of 5G, it's an amalgamation of all of these different or heterogeneous systems that can be configured in a flexible way to address different use cases. And just a side note, and whenever we start talking about flexibility in choice in anything in life, it always leads to complexity. So this is the story that we're going to paint in this seminar. The conception of during the conception of 5G, it is broken down into three major requirements of the system, to include enhanced mobile broadband, which means high-speed connectivity for smartphones; massive machine-type communications, which is the idea of having millions of devices connected to the system with high connection density. That's our Internet of Things component, or sensors. And the third requirement is to support ultra-reliable, low-latency communications, to support possibly vehicle-to-vehicle communications, Industry 4.0 or industry automation, remote healthcare, or other mission-critical type applications. As you can see from this diagram, 5G is pretty difficult to define. It's a catch-all communication system to address different verticals, including industrial, transportation, healthcare, and it moves outside of our traditional telecommunications networks. In our original definition of the 5G system, it looked at how 5G, or in this diagram that we have here, IMT 2020, needed higher requirements than 4G. Or, oops, I'm sorry, maybe sorry, this is the correct slide. Just 5G or IMT 2020 has higher requirements than 4G or IMT Advanced. So just a couple of spotlights here. An increased peak data rate from 1 gigabit per second to 20 gigabits per second, a reduction of latency from tens of milliseconds to less than 1 millisecond, and a possible 100-time gain in network energy efficiency. If you keep going on to this next diagram, though, you can see that different applications or different application requirements don't require all of their metrics to be capped out. They don't need to be the highest for all applications. So, for example, when we're thinking of IoT, we might need really high connection density, but then the amount of data that's needed to be sent, let's say, per month might be low, and the required peak data rate would be low. Furthermore, in those types of applications, we're looking even more for sustaining long battery life, so that the sensors or whatever that device is can be deployed and not touched for many, many years. Ultra-reliable, low-latency communications, we're thinking along the lines of self-driving vehicles, where we need quick reaction times at pretty high speeds, not necessarily really high peak data rates. So when we look at this and we think about all of these different user devices that can be on our network, the dimensions, the rate, and the variability of the types of data or the data that's coming from all of the user equipment on the network is growing exponentially. All right. So how does 5G accomplish this feat? There are a number of developments happening in the core network, namely the virtualization of the core, and it is now supporting a service-based architecture. And so we've seen a lot of commercial uptake in this area right now, especially with Amazon and Microsoft investing heavily in building out 5G cores, and they made a lot of investments last year around March or April of 2020. The second major core development is the disaggregation of the core network. And what are we seeing here? We're seeing that there's a separation of the control plane and user plane, which is leading us to have different backhaul options, which can be based on application. So if you're familiar with some of the 5G concepts, it's not necessary to be, but I'm referring to eCPRI and the different functional splits for delivering radio access network, different versions of the radio access network. I'm also talking about the ability to support edge computing, which brings processing physically closer to the user in the system. So that provides that advantage of possibly offering specialized low latency connections and processing. However, on the radio access network side, we're referring to, when we say radio access network, the RAN, the radio access network, RAN, we're referring to the radio connections in the network. 5G has brought on some new developments. The RAN developments that I think have had the biggest impact on our wireless systems is, one, the introduction of millimeter frequencies and bandwidths. Two, new antenna technology, which combines multi-user MIMO and beamforming to create something called massive MIMO. And we'll talk about what the words that I'm talking about, what they mean in later slides. And lastly, a ton of different possible RAN architectures, which include device-to-device links. We're going to spend some time talking about all of these different RAN developments before looking at how machine learning can help deal with the complexity introduced by each one of these components. As discussed before, we're now dealing with 3 different frequency bands: sub 3 gigahertz, which is well known to the mobile operators across the world, 3.5 gigahertz, which is now our new set of 5G frequency channels that are being rolled out right now, and then the high band, which is above 24 gigahertz. As you can see in the lower bands, they're good for coverage, mobility, and reliability of the signal, where in the high bands, we're providing a larger bandwidth or channel, and we can offer higher throughput and capacity in those bands. At the low bands, we're talking about smaller bandwidth channels, around 20 megahertz, which is what we have with LTE. In the mid-band, we're talking about larger channel sizes that are capped at 100 megahertz. So just to put things into perspective, 100 megahertz channel can carry 5 times more data rate than a 20 megahertz channel. It's a linear relationship between those two, between bandwidth and between bandwidth and data rate. And when we go up to FR2, or the high band frequencies, the channel bandwidths can go up to 400 megahertz. And even those channel bandwidths aren't really the limit of what we can do, because there's this idea of something called carrier aggregation, where we can take multiple channels and combine them and send them together to a user device, which means that in effect, what we'll be doing is multiplying our achievable data rates by, let's say, 2 component carriers would mean 2 times the data rate, or 4 component carriers would mean 4 times the data rate. And so you can multiply your achievable data rates. When it comes to the implementation of the system, the high band brings a different science and propagation feature to the system. High band is referred to as millimeter wave because the wavelengths associated with those frequencies are in the millimeter range. And when we start looking at those higher frequencies, components and the environment start to act differently. At low frequencies, engineers don't need to account for the phase properties of the wavelength, since the wavelength and the lower frequencies are large in comparison to component size or aspects within the environment. But when we start looking at millimeter wave, the wave properties of the signal, the phase properties of the signal have to be considered. Because when you have smaller obstacles in your environment, even you think about like paint ripples in the wall, where you have dimensions in and around that millimeter range, that scatters the signal a lot differently when you're looking at millimeter wave versus the lower frequencies or those longer wavelengths. So smaller obstacles, what I'm trying to say is that smaller obstacles on the scale of millimeters in the environment will have profound effects on the propagation of the signal, making adding additional challenges to site planning or system rollout. The second major technology advancement for the RAN is the introduction of massive MIMO. With respect to massive MIMO, there's new complexity in the antenna technology, which now integrates RF chains into RF transmitter chains into the antenna. So each one of those individual transmitter chains are responsible for beamforming and providing multiple in, multiple out services. So MIMO services at the same time. So they do both. So then the receiver chains implement the beamforming and also support the MIMO technology as well. If you're interested in looking at the ins and outs of antenna design and what's happening with respect to the system and all of that, I did a talk in this webinar series back in June that really talks about Release 16 and the testing challenges, and it talks about massive MIMO and beamforming and how it all works and the definitions of everything. In this talk, though, we'll just talk about the capabilities of massive MIMO and define it. So massive MIMO is the combination of MIMO technology and beamforming into one antenna unit. So for each massive MIMO antenna, it's constructed from multiple antenna arrays where each array can produce its own beam, which supports this idea of beamforming. On top of that, so really what we're saying is that a big antenna might have 64 elements, and we can break up those elements into, let's say, 4x4 antenna. It's 4x4 elements, so 16 elements. So then you can maybe support let's say 4 different antennas within that bigger antenna. And so in each one of those sub-antenna arrays can create a beam. And so on top of that, now you have multiple in, multiple out. So then the idea in the RF environment is that if you're able to transmit multiple uncorrelated signals to each other, to a receiver, we can decode those multiple signals, allowing us to receive separate data streams over the same air interface. So how is that implemented? Generally, if we're talking, let's just talk about something simple like 2x2 MIMO. We can have different polarizations on our antenna interface where now each polarization carries a different data stream. And so the receiver will be able to say, well, this data stream is from this polarization and this other data stream is from the other polarization. So then in effect, we're using the same frequencies and we're able to determine 2 different data streams over the same interface, as long as the signal that's coming to it is not correlated with each other. So when we talk about that, that's kind of the description of single user MIMO. And that's what we see in today's Wi-Fi routers or even our current LTE sites. So we can, per site, we can possibly double or quadruple our data rate per site because of MIMO, in this case, single user MIMO. However, now that we have beamforming on top of this, we might be able to replicate this several times per site. So now the idea being is that we can have multiple beams on the same site using the same physical resource. So the same in this talk we're talking about is OFDM subcarriers. So we can use the same OFDM subcarriers to transmit information to, let's say, the top user in this diagram and to the bottom user in this diagram, as long as the frequencies, the channels are isolated from each other spatially. So then now the same frequencies can go to user 1 and user 3, and as long as they don't interfere, then in effect what we're doing is reusing the same frequencies within the same site. And then let's say user 2 there, the one in the middle, probably you wouldn't use the same frequency set as the top user, because that beam 2 and beam 3 probably would interfere with each other. So then you wouldn't be able to reuse the frequency again there. So anyhow, the overall effect is that we can reuse the same frequencies over and over again within the same site. And so that gives us this idea of multi-user MIMO. So multi-user MIMO doesn't actually increase the data rate going to each individual user, but it does increase the data rate that the entire site can support. So going a little bit further into how MIMO works, we rely a lot on signal encoding. In the old communication paradigms, this is actually something from GSM here, we would send our data along with a training sequence. And then what ends up happening is that training sequence will go to the phone, and the phone knows what the training sequence is. It will train a digital signal processor on there. So then what it'll do is say, so base station sends the signal, the environment messes the signal up, it gets to the phone says, I'm expecting this, and it unmesses up the training sequence. So then it trains the DSP, and then it uses that trained DSP to decode the data. So then in every single packet that comes through, we've got this training sequence overhead that's going on here. As opposed to the massive MIMO way. So in massive MIMO, it's slightly different because we encode the signal prior to sending it, and then the signal, as it should look, the signal actually should look good at the receiver. So in order for that to happen, the user device needs to send channel state information or feedback back to the transmitter. The transmitter uses that information and loads it into a pre-coding matrix so that it can encode multiple streams of data such that they don't interfere with each other and as they reach the final user. So overall, in conclusion about massive MIMO, you can see that there's a lot of new complexity in the antenna, new processing that needs to occur in the antenna, new algorithms to encode the channel, which overall tend to become more and more complex as we add more antenna elements, because each one of these pre-coding matrices are dealing with the signal or the beam with respect to the elements or the antenna elements that are in the antenna. So then as we add more elements, there's more coding that needs to happen in this interaction. All right. So far, we've talked about two of our 5G RAN developments. First, the addition of millimeter wave frequencies and bandwidths. Second, the addition of massive MIMO. And third, the third aspect of 5G RAN developments is the number of different topologies that are out there, which include device-to-device links. In this talk, though, I don't really want to talk about the differences between non-standalone and standalone deployment, but only to show you that there are different ways of deploying 5G networks with respect to evolution and rollout. And the idea being that when we have 5G, it's going to be part of a heterogeneous system, a heterogeneous network, meaning that it will coexist with other technologies, including those of 3GP and non-3GP, 3GPP. And we'll see for the next several years, new technologies, new services, new RAN features and parameters, they'll all be introduced at an ever-increasing pace. The traffic patterns will not be static and will change frequently in both in time and over geographic region. So just to outline this a little bit more, one of the most common topologies that are being rolled out right now, as we talk about it, I just want to outline that it's just a phase of deployment. It's a pathway to evolve the network. This is a type of hybrid. This type of hybrid deployment will always exist. If not with 4G and 5G, maybe with 5G and 6G, or 5G and some other type of system, some other type of radio technology. So in this one, this is called inter-RAT dual connectivity carrier aggregation. So inter-RAT refers to the putting in 4G and 5G different radio access technologies. Dual connectivity means that it's connected to both 4G and 5G system at the same time. And carrier aggregation means that it's sending channels from multiple channels from that's being received at the phone. So this is one of the possible deployment scenarios that's popular today. But when we look into the future, which is what this talk is about, we'll always need to deal with this type of complexity. Now, as part of Release 17, we've got this idea, this new concept of integrated access and backhaul, where we might have a fiber backhaul connected to a donor site, which can provide a microwave backhaul for a number of different sites, possibly remote sites or small cells. And from there, it can be either multi-hop connection or redundant links. All of that can be built into this integrated access and backhaul specification that's being rolled out right now, or not even rolled out, but released in Release 17. And so the frequencies of the backhaul can also be used for access, so mobile access or fixed wireless access. In order to support different verticals, like what I show here are wearable devices or logistics, there's a new release around 5G New Radio called Sidelink. New radio, it's called NR Lite, called Sidelink, which now allows for a repeater topology. So then now, for example, we might have a truck with a number of sensors that are low powered and they need to connect back to the wide area network. They might be low powered, might be in a container which doesn't allow signal penetration. They can connect to the wide area network via a relay. Another use case are wearable devices. So the wearable device, you might not want, it can maybe connect directly to the wide area network, or if you want to conserve power, you might consider that it should connect to the cell phone and from the cell phone to the wide area network, using that the user's device as a relay, in this case, the handset. These devices can be tethered to the relay that's connected to the wide area network. There's studies going on in Release 17, Release 18, talking about how do you tether the device. And so there's a couple of different options here. There's a layer 3 connectivity where there's a special connection between the UE and our wearable device. And that connection between the UE and the wearable device might be Bluetooth or Wi-Fi or some other technology. Or it can even be a 5G technology that's being produced, like a 5G hotspot that's being produced from the cell phone. That's still to be studied. Or the other option is a layer 2 connectivity. A layer 2 connectivity is that now the handset works as a relay, and then that relay it will provide act as a bridge between the wide area network, the 5G cell site, and the wearable device. And so that in that scenario, then it's actually the wide area network is providing direct connection to the wearable device, which means that 5G can offer quality of service to that device. Maybe we don't see the need for that right now, but maybe in the future we will have applications that do need that. And just recently, I've been exposed to this talk about non-terrestrial networks. There are a couple different topologies that are being discussed. One where the satellite is being used as a backhaul. One where the satellite is just is transmitting G-node B information to a device where the G-node B is on the ground, or when the G-node B or that 5G base station is integrated into the satellite. So now, when we're zooming out to the bigger picture here, I think we've just outlined so many new ways that 5G is allowing connections to devices, allowing for different devices to connect to the system, and all of those topologies need to be kind of maintained in some sort of way. So over the last 10 slides or so, I hope that I've outlined the amount of new complexity that will be introduced in the 5G radio access network, from beamforming and massive MIMO to the number of different frequency channels that have different attributes, and the possible overlapping and interacting topologies that can be present. All of that needs to be managed within your 5G system. All right. So we've looked at some of the advances in the radio access network through 3GPP releases. Now we're going to move on to the role that machine learning can play in optimizing 5G. There isn't too much written in this area, nor are there companies that are contributing publicly to machine learning capabilities with respect to 5G. The thing about machine learning is that it's doing its best work when it's entirely invisible to the user. So what I'm going to do in this section is to talk about the relationship between 5G and machine learning. We're going to look at how decisions are made currently in 5G and how we can improve decision-making using machine learning. Or another way of framing that sentence, improving decision-making using machine learning, we're going to look at how data-driven problem solving can help with 5G operation. So overall, when we look at the optimization of 5G, we have to understand the processes that make 5G work. So I've made a list here that machine learning could potentially be applied to, and the list is in order of, I've put it in the order of the 5G deployment lifecycle. So overall, when we look at the ways that in which devices connect to the system, we need more effective ways of coverage design, ensuring devices have access to frequencies, bandwidths, and latencies required for their application in their geographic location. The backhaul design kind of goes hand in hand with coverage design. Each one of those topologies that we mentioned in the slides before need to be optimized to ensure that each type of application sitting on the 5G system is thinking about that robustness and latency values. The network, on top of that, will need to be able to scale as the demand on it increases or decreases, and we need to be able to provide end-to-end services that have pretty strict performance requirements. Moving into the radio access network, there needs to be efficient channel and resource allocation to different types of devices. And lastly, we need to ensure that with respect to channel feedback mechanisms, we're able to do some sort of, we'll see examples of how we can use machine learning to decrease the amount of overhead on the air interface, affecting air interface encoding. So when we look at 5G and the challenges that are present when deploying a robust and efficient network, the strengths of 5G the strengths of AI complement the challenges of 5G. So for example, 5G presents us with a lot of hard-to-model problems, especially around the air interface and traffic predictions. AI can provide data-driven problem solving. 5G needs effective parameter optimization, which generally the way that it works now is that we have discrete values that are stored in code books or modulation encoding schemes. However, when we use AI or machine learning, we can make predictions and simplify those processes in order to achieve any one of many goals. So like if we're able to predict what's going to happen as opposed to communicate what is happening, we can lower the complexity of receivers, we can reduce the overhead that happens on the air interface. Lastly, 5G has hard-coded decision-making according to the specifications that rely solely on the measurements being made by the phone or the decision-making algorithms in the base station. However, there's an additional layer of information that's available that can be used to inform decision-making, which is contextual awareness. What do I mean by contextual awareness? It's those other factors that affect the decisions that a phone makes. So, for example, modeling and predicting what other devices in the network are doing. Adding new factors for decision-making like geographic reason, topology, velocity, or even understanding what kind of device it is and what application's running on it. So is it an IoT device? Is it a smart device? Is it augmented reality glasses or surgical control? Because each one of those applications will have a predefined traffic pattern that's predictable and doesn't necessarily need to be scheduled as packets come up, which when you do that reactionary type of scheduling, there's a lot of overhead and processing that need to occur because of that. All right, so I was just going to talk a little bit about some definitions of what do we mean by artificial intelligence, machine learning, deep learning. Here are some definitions. So like artificial intelligence, it refers to the ability to solve tasks that require human intelligence. I'm not going to be talking about this. I said AI before, but it's not really AI. What we're going to be talking about is machine learning, which is just one aspect of AI. It helps perform specific tasks by learning from data and making predictions. And then we have deep learning, which is one set of algorithms that can be used to inform a machine learning model. So actually this topic, we're really going to be talking about machine learning and not AI. In general, machine learning uses an algorithm in which data is fed into it and trains that algorithm. And after the algorithm is trained and tested, you're left with a machine learning model that takes inputs and provides predictions or results as an output. You can see from this process why we consider machine learning as a data-driven problem solver. Just taking it one step further, there are many different types of machine learning algorithms. However, I'm just going to talk about one of them here, and this is deep reinforcement learning. Because from my feeling and what I've read and all of that, this can potentially apply to a lot of the problems that we're trying to solve with 5G. So deep reinforcement learning works on the idea of actions and rewards where the algorithm measures the amount of reward it gets for each action. And then it tries and maximizes its reward. So I'll say that again. It creates actions, it measures the amount of reward that it gets, and it tries to maximize its reward. So if you haven't done anything in machine learning or AI in the past, I do suggest that you watch this documentary. It's DeepMind's AlphaGo. It's on YouTube. It's 2 hours, and you'll learn more about deep reinforcement learning and machine learning in those 2 hours than you can learn anywhere else in any sort of environment. It's really good. So just moving on here, this next slide is a little bit more explicit about the phases of machine learning, where an algorithm goes through a training phase to learn appropriate outputs and then begins to create a model. And a little bit of the nitty-gritty there, when we say deep in deep learning, we're referring to the number of layers that the algorithm has. As the prediction is going through different layers of the algorithm assigns weights to each one of the different pathways that can possibly happen to the next layer. And if a result is an error in the training phase, what will happen is that error will propagate backwards through the layers and adjust the model weight, probably lower the model, not probably, will lower the model weight for each one of those pathways. And then after enough training of the model happens, then it can be put into operation. And by inputting new data in production, the result is called an inference. And that's defined as the conclusion based on evidence and reasoning. So they use the word inference for machine learning. So now taking that back, and now let's go back to our 5G system. We've got key performance indicators. And these key performance indicators could potentially be the rewards that reward aspect that the machine learning algorithms are applied to in 5G. So for each one of these performance indicators, there's actually a combination of different metrics that are already collected within the 5G system. So for example, all of these KPIs describe that all the aspects needed to satisfy the different 5G use cases of enhanced mobile broadband, ultra-low latency connections, and massive machine-type communication. So I'll just go through, we're running low on time, we've got 10 minutes. So I'll just run through a couple of these performance indicators as opposed to going through all of them. So for example, maybe the accessibility KPI will refer to the ability of a device to register and obtain service. So that would include sort of radio link failure that's happening over the air interface, all the way to the ratio of successfully performed registration versus attempts in the 5G core. So that's one of them. Let's see which other one. Maybe utilization. So utilization, the utilization KPI looks at maximizing the physical resource usage without affecting the end user experience. So when you look at, if you read through these different key performance indicators and you add them all up together, they lead to potential rewards for a deep learning algorithm. All right. So in 5G, what else can go into this decision making? So the way that it's working is that currently handsets are working on their own, and they're coordinated at the G node Bs, the 5G base stations, and they work on the usage, but they work in a usage environment. So then what I'm saying here is that it works in an environment, and that environment is pretty statistically predictable. The system, what the system's missing is some forms of contextual awareness, knowing the type of device, the predicted traffic patterns of that device, the amount of movement that might be coming from that device, the applications running it, and also the actual environment. So what obstacles are in and around it? So based on all of the sensor data and possibly mapping data, there's a lot of information that can be put into what can be used to make decisions. And lastly, resource allocation on demand. It can be allocated on demand. Resource allocation is usually allocated on demand and is divided into each subnetwork. So then the radio access has its own set of numbers, and backhaul has its own set of numbers, and core network has its own set of numbers. And so that end-to-end system allocation and usage can possibly be added into the decisions. When we start looking at decisions being informed by analytics instead of the immediate environment, which is kind of a proactive versus reactive decision-making process, a lot of system overhead and a lot of system efficiency can be gained. All right, so let's look at some tangible machine learning solutions that have been provided. Qualcomm came out, did a recent study where they did a demonstration where they looked at mobile 5G millimeter wave beam prediction. So they used on-device machine learning models, and they've shown that a user device is able to predict its RSRP, which is its signal power, signal strength, and the millimeter wave beam that it should be camped on, using not only normal 5G processes, but using the various sensors and positioning data that the phone had to predict when handovers should happen. The results of being able to predict its beam and RSRP means that it can be applied to optimizing the network. So we know from Qualcomm's experiments, they know that they can predict RSRP and beam choice. Now that information now can be applied to improving the system, which means that you can possibly move more seamlessly through the network. You can reduce network loading. You can have lower receiver complexity. You can do better link adaptation. Overall, you can reduce the amount of raw data that needs to be sent over the network. All right, and so the next application could be with respect to system deployment. So when we look at site planning, we base it all on this RF propagation model. This model is pretty static for planning purposes. You can see it's got two main factors. It's got distance and frequency. So there are three different coefficients, alpha, beta, and gamma in there, and they're derived from empirical data. So what does that mean? That means that we find a model environment, our model city, let's say. We do a lot of drive testing in there, and we change the coefficients so that it fits the data points. So we're kind of, I think it's called regression, fitting the line to the data. So we change those numbers in order to do that. And then, so the last term in that equation is the statistical standard deviation from the model based on fluctuations in the environment. In terms of planning, this equation shows us that in order to determine coverage, it can determine coverage pretty well as long as our environment that we're planning in is very similar to the model environment that the model was made of, which might not be the case. When we design new 5G systems, there's a lot more complexity in there. We have site selection, which is partially a real estate issue. We've got different frequencies that have different propagation distances, data rates, and potential latency values. We have different topologies that need to be considered, and the number of options for deployment and number of services that need to be supported are exponentially increasing. So overall, when we look at the system deployment side of it, machine learning can be applied to solving this problem because it's going to be very complex to envision. All right, so right now I'm just in summary now. So right now we've talked about 5G and the challenges of optimizing it. I'm hoping that you can start to see some of the places where machine learning can be applied to solve some of the problems that we're going to envision for future 5G optimization on the road to 6G.
All right, great. Thank you very much, Kevin. We don't have a lot of time left, but a question here from the audience. Question is, won't using satellite as a backhaul affect the stringent latency stipulation for 5G?
Yeah. Hi, Bill. Yeah, so for sure, there is going to be, everything is about use case. So when we talk about the use cases for satellite backhaul for 5G, we're not talking about ultra reliable, low latency communications. We'll be talking about just providing service which can accept a high latency connection. So overall, going back to one of the earlier slides, looking at the different 5G requirements and what requires what, I think that's just in the, let's see, I think it's this one here. Just looking at this slide here, you can see that latency is not a big factor for some of the types of 5G requirements, and satellite will affect that for sure.
Okay, great. I think we'll wrap it up there. I do want to put out the, let me just push this last slide out. This is the PDH certificate code for those of you who are getting an education certificate with today's webinar. We are out of time. As I indicated earlier, the session will be archived in about 24 hours, and once the archived webinar is available, a notification email will be sent to all the registrants. I'd like to thank Kevin for making this such an informative hour and for his contributions all along the year on this webinar series, The Road to 6G. I'd like to thank our sponsor and thank our audience for participating in today's session. And we hope you found today's event valuable and will return for future IEEE Spectrum Online webcasts. Thank you.
Thank you, everyone.